Welcome, I'm Mingzhe from Tsinghua University. Here I'll talk about a systematic approach towards more efficient and correct instrumentation in fuzzing. Fuzzing is a popular approach in detecting bugs. For example, when testing a PNG decoder, a fuzzer generates lots of random inputs to exercise the target program. If the program demonstrates abnormal behavior, then a bug is likely found. However, random inputs are unlikely to trigger interesting program behaviors and bugs. Instrumentation can be used to improve the effectiveness. By injecting props into the target program, instrumentation enhances fuzzing in many ways. For example, the left side presents a typical parser for PNG images. It reads the file header into memory, checks for header validity, and decompresses the image finally. How can we improve fuzzing with props? First, we can inject props into the file read to see if the memory write is illegal. To resolve complex constraints, we can use a prop to record the operands to assist input generation. More importantly, we can collect cause coverage to prioritize inputs with previously unknown program behaviors. However, instrumentation props come at a cost. For example, address sanitizer, which checks for memory bugs, incurs a 2 times overhead. Collecting cause coverage also incurs similar penalties. One reason behind the overhead is that the code injected by instrumentation does not play well with optimizations. Below is a simple code snippet which calculates the sum of an integer array. Modern compilers tend to vectorize the loop to accelerate the calculation with hardware. Inside the function, there's an array access which could be illegal. To catch such bugs during fuzzing, address sanitizer injects runtime checks, which may abort the program. After instrumentation, the compiler cannot know whether the program will be aborted for each loop iteration. Consequently, loop vectorizer cannot apply optimization here, and significant performance loss is expected. As a workaround of missed optimizations, compilers commonly instrument the program as late as possible. However, this creates a new problem. As the control flow graph shows, the optimized program has 2 times 6 times more edges than the original program because of the loop vectorization. Suppose that we are collecting edge coverage. The extra edges create unnecessary feedback for fuzzing. The root cause is that the transforms performed optimizations do not preserve the fuzzing critical semantics. Besides compile-time instrumentation, the compiled program can be patched at runtime. For example, to collect code coverage, we can directly replace a program's original instructions with software breakpoints. The replaced instruction triggers unique signals when executed. The fuzzer then resets the instruction and resumes the execution. This approach ensures absolute zero overhead if the props are unremoved. However, machine code loses even more semantic information during code lowering. Consequently, this approach cannot be easily applied to complex instrumentation schemes. In summary, there are conflicting goals in instrumentation. For semantic correctness, the original IR directly generated by the compiler front ends is the only choice. However, instrumentation itself harms the optimizations. On the other hand, rewriting the machine code ensures the lowest overhead. However, semantic correctness cannot be ensured, and complex instrumentation can be difficult to implement. Since no instrumentation approach can achieve all these goals simultaneously, modern compilers usually instrument the optimized IR as a compromise. How can we achieve all these goals? Analyze the table carefully, and we can find the root cause for the benefits. With raw IR, the semantic correctness and instrumentation capability can be preserved. With dynamic instrumentation, the unnecessary props can be removed during fuzzing, and the overhead can be reduced consequently. How about combining these designs? We propose Odin, an on-demand instrumentation framework to achieve both conflicting goals. Compared to existing instrumentation pipelines, which only instrument the program for once, Odin tweaks the instrumentation schemes during fuzzing continuously. Specifically, the fuzzer can freely change the props according to the fuzzing feedback. Odin then recompiles the executable on the fly to apply the changes. Still, there remains one challenge. Rebuilding a system can take minutes to complete. How can we reduce the additionally introduced overhead in recompilation? Below presents a breakdown of compilation cost on a small library, libxml2. The initialization of the build system consists of the autogen and configure script. After the initialization, each source file is processed by the compiler's front end to generate LLVM IR. The IR is then optimized to generate machine code. At last, the linker produces an executable file. Because Odin operates on the raw IR generated by clone, we can directly skip the autogen, configure, and the front-end part. Despite this, a rebuild still costs dozens of seconds. An obvious approach would be reduce the recompilation scope by only recompiling the changed props. The overall procedure of Odin can be clearly illustrated from the aspect of the fuzzer. Odin is implemented as a library to cooperate with the fuzzer closely. Before fuzzing starts, Odin creates a partition scheme for the program. The fragment definition describes the boundary between fragments. The fuzzer maintains the global prop state to describe the instrumentation requirements. When the fuzzer requests a recompilation, Odin schedules the whole process according to the prop state. The scheduler locates the fragments to change and creates a temporary IR encompassing all of them. Next, it instruments the temporary IR by applying the custom patch logic. After the fuzzer's patch logic completes the instrumentation, the instrumented IR is then split to small units according to the fragment definition. Finally, the LLVM infrastructure is reused for optimized code generation. We finally use the lowered code cache to link to a new executable. The fuzz engine generates inputs for the target executable and receives feedback from it. With proper feedback, the global prop state can be updated. For example, the fetch engine can mark unused props as redundant. The above steps are essentially a feedback-driven loop. In this way, the fuzzer can continuously tweak the instrumentation scheme during fuzzing. Fragment definition plays a crucial role in recompilation. How should we position the program during the pre-instrumentation survey? A naive option would be generating one function per fragment. However, if we only recompile the changed function, many optimizations can be missed because they require multiple symbols. Take a look at the code snippet. The function main calls function foo, but the argument is never used. The dead argument elimination optimization removes unused parameter. It also removes the corresponding argument inside the caller. In other words, the inter-procedure optimization requires both the caller and the callee to present to proceed. Similarly, the printf inside function foo can be optimized to put s. In this case, the trailing new line of the associated unnamed constant should be removed. In summary, if we simply recompile single functions, the many kinds of optimizations would not run. How can we prevent missed optimizations when partitioning? The key idea is to know the constraints limiting optimizations. For example, the function negate should be optimized by stripping the dead argument. Here, we mark it as bound to cluster it with all its potential users. The global constant format can be duplicated when needed. Here, we mark it as copy on use to duplicate to the user's fragments, allowing intra-procedure optimizations. The remaining symbols does not affect optimization at all. To reduce the recompilation scope, We define them as is for a stable ABI. To generate such classification, we first run a trial optimization and collect optimization path's behaviors. With the classification results, we can build fragments according to the optimization constraints. Inside one fragment, a symbol can be defined for local use only. It can be also exported or imported for cross-referencing. We first create initial fragments. The special case, bound, is handled first. The other fixed symbols are then added. Since cross-referencing is not resolved yet, we import the reference symbols and internalize the export symbols if they are not referenced by other symbols. The pre-instrumentation way partitions the program into fragments. The fragments are used for all subsequent recompilations. Since the minimum recompilation unit in Odin is a fragment, modifications to functions should be converted to fragments. For example, suppose that the target program contains 4 symbols. The pre-instrumentation way partitions them into 3 fragments. Note that both bar and base occur in 2 fragments. Suppose that the father requests to re-instrument function bar. Because function bar is used by both fragment 0 and fragment 1, we should recompile both fragments. We clone the related 3 functions into a temporary IR. Next, the instrumentation logic is invoked to update the cloned functions on the temporary IR. After the temporary IR is available, code generation can be started. We first split the temporary IR according to the fragment definition. Each fragment's IR is generated to code with optimizations. The result machine code is used to update the code cache. Here, all the cache code is up to date. We can link them to produce the final executable file. For evaluation, we compare Odin with 2 baseline variants. Odin 1 partition does not partition the program at all. The raw IR is directly used to generate code. Here, optimizations will never be affected by partitioning. On the other hand, Odin max partition splits the program into as many fragments as possible. This design ensures the fastest compilation speed. We first find that Odin greatly reduces the recompilation cost. While it is 7 times slower than the fastest possible max partition scheme, Odin still shaves 98% of the overall recompilation cost. Second, while time saving is significant, Odin does not degrade the code quality too much. When compared to Odin 1 partition, the best possible optimization scheme, Odin is less than 1% slower. To demonstrate the power of Odin, we implement Odin Conf to collect code coverage. Specifically, Odin Conf uses on-demand instrumentation to prune the useless profs during fuzzing. The compared baseline tools encompass a variety of dynamic and static tools targeting different program representations. Compared with classic coverage tools, Odin lowers the overhead to a mere 3%. In other words, Odin Conf coverage collection efficiency is 3 times better than SANCOF and 17 times better than Dr. Conf. In summary, we propose on-demand instrumentation, a feedback-driven instrumentation approach over raw IR. It achieves low runtime overhead while preserving correctness. To implement on-demand instrumentation with low overhead in recompilations, we use on-the-fly recompilation. The key idea is to partition the program with optimization awareness. In evaluation, we find that Odin shaves 98% of the recompilation duration. The overhead of compiled programs is merely 1%. That's all. Thank you. Any questions?
Thank you so much for the talk. So again, if there are any questions, you can post them on Slack, or you can come in the orange circle where I'm at and gather. While we wait for some questions to pop on Slack, I have a few. So I was curious about, in the evaluation, you described this max partition. I was just going to ask about how successful partitioning is than you talked about in the evaluation. So great choice of research questions. But I was just curious how the max partitioning is determined and how it can be semantically correct, because the examples you seem to be like you would bond things together, because if you didn't bond them together, then you would end up with miscompiled things. So how is this max partitioning? How does max partitioning work?
So basically, we have two variants for the original Odin, and one variant is one partition. We do not partition the program at all. So basically, it just looks like LTO version, which in this case, we just recompile the program as a whole large base code. So, and the opposite would be splitting the program as much as possible. For example, you may have 3 functions. The functions may try to call each other, and there can be inlining, unrolling, and many optimization involved. And Odin can detect the optimization that happened and tries to place the 3 functions inside one module if possible. That's the original version. So if we try to evaluate the partition strategy, we would like to split the functions as much as possible. So we just simply create 3 separate modules and compile the 3 functions separately. So in this way, we can reduce the compilation's cost. Yeah.
So the maximum partitioning is really at the function level.
Yeah. We try to split the functions into many modules and compile them separately. In this case, we can ensure the minimum possible recompilation time. So it's a baseline for the recompilation performance evaluation.
Right. So what is the level at which these probes that you have can be written? Are they at the level of instructions or of functions? I know sometimes when people write fuzzer instrumentations, you're looping over various different parts of the IR. So what is the interface you have for writing these probes?
Yeah, that's a good question. So currently, we just define the boundary of recompilation at function level. It's clear because the OS ABI is clearly defined. You can simply recompile separate functions without interfering with others. So currently, the minimum recompilation unit is a function. So frankly, there are some impact caused by this decision because for some large projects, you may have many small functions inlined into a large function. So the performance of recompiling the large function can be degraded by this decision. But we believe it's a reasonable one because have a well-defined ABI between the recompilation units is very important.
Right. Okay, tiny question. Can you do link time optimization things with this? Because I know a big problem with AFL Go, for instance, was that it was very slow at compiling for different distances. So would you be able to do things across the call graph with Odin?
Yeah, so basically the idea is that we have a large program, bitcode, and we try to split it when you instrument it. So if you instrument it at the LTO level, you can enjoy the whole program observation. But once you try to compile the program with Odin, the recompilation cost and the initial code generation cost can be vastly reduced, even if that you are using LTO to optimize your fuzzing process.
All right, that sounds great. Yeah, I look forward to looking more into this after the talks.